Hey everybody, this is Harsh. Today I'll be talking about GeoSwarm, which is a multi-source download scheme for a peer-to-peer location-based service. Location-based services are software applications that use location data to control features. With the gaining popularity of GPS and internet readily available in portable devices such as mobile phones, laptops, PCs, location-based services are becoming really popular. Few examples of location-based services are Foursquare, Facebook, Places, etc. The current limitation of location-based services are they're based on cloud architecture. That is, the server-centric. They come with their own limitations, such as high costs. Well, it's not easy to host something on the cloud. B, centralized architecture is always susceptible to privacy issues. So if a file were to be hosted on a server somewhere on the cloud and the server were to be compromised, the file would be compromised as well. So a simple question that comes to our mind is why not use BitTorrent for a location-based service? BitTorrent is a peer-to-peer system, so it's non-server centric. It handles asymmetric network connections pretty well as well. The main drawback here being location-based services need to have persistent storage, and BitTorrent doesn't support that. Hence, BitTorrent needs to be extended to provide replication and hence persistence. GeoSwarm is an overlay which supports location-based search. The addressing and routing is based on the peer's physical location, which can always be retrieved by the GPS on the device. It divides the location into a sphere, which is divided into n directions, and each direction is further divided into something known as distance buckets. The geographical area covered by a distance bucket increases exponentially with distance of the bucket. Hence, find information is available about peers neighbors which are in close proximity, and hence core space information is available about peer neighbors which are far away. So if you look at a GeoSwarm routing table, you can see that this peer is divided into n directions, which is in turn divided into distance bucket. The size of the distance bucket increases with the distance, and hence course information is available about neighbor peers as we move away from the peer. GeoSwarm supports the following functions: the find nodes, the store, and the area search. The find node requests the key closest peers to location L that are contained in the Bloom filter. The store requests an object O with location L being persisted by the overlay, which uses the find nodes method functionality. The area search request returns all the previously stored objects O that match the search term S and are located within a circle of radius R around the target location. Keep in mind, the Bloom filter here is a filter that helps us remove duplicate peers being returned. GeoSwarm is a reliable multi-source download scheme. It is built on top of BitTorrent and GeoSwarm. It is the reason why GeoSwarm is not sufficient for location-based search is it does not support the persistence of larger multimedia objects. It supports the persistence of only smaller objects. GeoSwarm, on the other hand, ensures reliable storage and fast retrieval of location-based data of size up to several megabytes. It achieves reliable storage via replication of location-based data and achieves fast retrieval using a location-aware multi-source download scheme, which we will talk about in the further slides. So the GeoSwarm system design can be first thought about as let's talk about the data model of GeoSwarm, data structure. So it consists of meta items media references, and meta chunks. Now, meta items are the meta information about the location-based data. It consists the geolocation, which is the latitude and longitude, which can be retrieved by the GPS, the unique ID, which is the SHA-1 or the MD5 hash, and media references. The media references are meta information about the media object. So media references point to media chunks, and media chunks together form a media object. The media references contain a unique identifier itself, the media object size, and the peers list. So the list of peers storing the media object. This includes the geolocation, the IP, and the port. Looking at this data structure makes it much more clear. The media object O is divided into media chunks, so the combination of chunks C1 to Cn gives us the media object O back. Each media object has a media object ID, which is unique. The meta item M contains information, the meta item ID, the geographical location, the description, and the tags. The media references point to the media chunks and also point to the media object itself. Let's look at how data is published in a GeoSwarm. Suppose a peer P needs to store a media object O. It calls the store method to store the media object O. Now, as we saw in the slide behind, a media object is split into chunks. From there, the media reference is derived and attached to the meta item M. Based on the location, we determine the key closest peers to peer P. And for each peer Q that belongs to this returned list, the store method is called, passing the meta item and the location. The set of peers that participate in this publishing process is called a GeoSwarm. Now, since a set of Q peers are going to make a download request to peer P for the media object, we have to ensure a way that the peer P is not flooded with requests. Now, this can be done using two ways. The first way is each of the K peers initiate a random backoff. So they back off for a certain amount of time, after which they make a request to peer P to get the media object. The second way is peer P limits its parallel upload slots. So as soon as the upload slots are full, it does not accept any incoming requests. Now we should remember that peer Q initiates the download by requesting chunks in a rarest random fashion. If you've seen with the working of BitTorrent, such algorithms ensure that replication is followed and we have a good download throughput. In this section, we study about how we can download a media object from the GeoSwarm. So peer P issues a search request and waits for the meta item M. For each M which is returned in the list of meta items, we look for the attached media references. We compute a distribution of the media chunks required to get hold of the entire media object. And we request these media chunks in the rarest random first fashion. So for each successful download of the media object, we add a new replica to the system. The peers which go offline are marked as left, and this helps us to prevent timeouts for future requests. In this section, we study about replicating location-based data. Well, here in the GeoSwarm, two types of information needs to be replicated. The first is the meta items replication. The second is the media object replication. The media object replication here is the replication of the multimedia content itself. As we studied earlier, the meta items is nothing but a meta information, and these are relatively small in size, and hence have really low overhead for proactive replication. Peers send probe messages to check for the availability of the meta item. Peers which do not have the meta item respond to the probe message and issue a request to get the missing item. The same cannot be done for media object replication, however. The reason being, media objects are larger in size. If we were to maintain k replicas for each meta item for a media object, then that would result in a really high traffic overhead. Hence, the k closest peer constraint is relaxed for the media object replication. Now, this relaxation helps us to reduce replication overhead and improves the performance of the system. The authors evaluate the system using a simulation. A total of 2,500 peers were used in this simulation, with each peer contributing a meta item and a media object. The size of a meta item was around 10 KB and the size of a media object was around 2048 KB. The upload and the download bandwidth of the peers were such that they resembled a DSL connection, which is pretty close to the real world scenario. The first evaluation the authors did was by varying the chunk size. So the size of chunks varied between 8 KB to 2 MBs. The study notices that smaller chunks lead to decreased download performance and increase in the number of download timeout requests, while large chunks lead to decreased download performance because there are not enough uploaders in the system. Hence, we need to find a trade-off. Here can be seen that for larger download chunks, the number of uploaders in the system go down, and hence download throughput goes down. Hence, we need to find a correct trade-off between a really small chunk size and a really large chunk size. The second criteria the authors variated were the number of replicas. So the replication factor K, also known as the configuration factor, it varied from 2, 3, 5, 10, and 20. A replication factor of 2 is sufficient to achieve a download success ratio of 1. Hence, high replication values is not needed for a higher success ratio. But to increase the maximum download throughput, a factor of K equal to 10 is necessary. In the third comparison, the authors vary the number of upload slots in the peers from 1 to 64. Using one upload slot causes significant impact to the success of the download ratio. The performance saturates when the upload slots are around 4 to 8, and it increases from 1 to 4 to 8. So the download success ratio increases as we transition from 1 upload slot to around 8 upload slots. But as the number of upload slots goes above 8, it decreases the download throughput. Hence, they conclude that 4 to 8 is an optimum number of slots needed for a peer in the GeoSwarm. The authors then vary the upload bandwidth on the peers and notice that the increase in the upload bandwidth helps in achieving higher download throughput, which is pretty obvious. It decreases the number of download requests, the number of rejected download requests, but it has no impact on the successful ratio of downloads, which is pretty expected. The final factor the authors vary is called the churn factor. They simulate that by successfully reducing the session and the intersession times. The success ratio decreases as the peers leave the system, and also the download throughput. To minimize the above parameters, the authors define that the replication is vital. Replication interval needs to be reduced. The lesser the replication period, the lesser the impact on the system. Since the media objects are replicated only on the available peers, it doesn't impact the publish phase much, since the chances of peers leaving while the media object is actually being replicated is pretty low. So GeoSwarm achieves geographical proximity of stored objects by combining A, the multi-source download scheme, something similar to what we get from BitTorrent, and the location-aware replication mechanism, which is built on top of GeoDemlia. The authors show that it helps achieve 100% benefit in download throughput compared to a single source download, and 95% of all the downloads are successful, even during churn. Thanks a lot for watching. Please be free to post any questions. Thank you.